Morning, friends. I'm Dr. Tyagarajan Satish Kumar, faculty in the Department of Biotechnology, Kumaraguru College of Technology. Today, I'm going to deal with mechanism of epidermal growth factor mediated signal transduction. My talk covers two different angles. One, different hallmarks of cancer. The second part, how epidermal growth factor can induce a cell division. Exclusively, how epidermal growth factor interacts with the receptor. That could be the main focus of my talk. What is cancer? Cancer can be defined as uncontrolled growth of cells, or cell is unable to stop its own division. So when there is a start signal, there should be a stop signal, right? There should be a start, there should be an end. So here there will be a very good start, but the start will be a very worst one in the sense cell is unable to stop its own division. So there will be uncontrollable mitosis. As a result, cell divides or proliferates continuously, which actually increase the uh, density of the cell, which we are terming as a cancer. So cancer is nothing but uncontrolled cell growth of cells or uncontrolled proliferation of abnormal cells in a particular part of an in vivo system. There is also another terminology or another term, tumor. Sometimes cancer is also referred as a tumor. So tumor here is nothing but swelling part of a body. You know that when there is an inflammation, then only we can expect a kind of swelling in an in vivo system. But here there is no inflammation, but still a kind of swelling will occur. So this swelling occurs due to the uncontrolled growth and increased mass of tissues. Swelling part of a body due to abnormal growth of tissue. So that is actually termed as tumor. You know, cancer is a genetic disease. Usually cancer is created or inculcated in the body due to repercussive or recurrence of repeated mutations which happens in a cell. So mutations may happen in a somatic cell or it may happen in a germline cell. If it is a somatic mutation that will ends with an individual, it will not pass to his generation. Whereas if that particular mutation has occurred in gametes, exclusively in sperm or ovum, then the damaged part of the DNA fragment will be transmitted to generations together. So please understand, cancer arise due to issues in the DNA. That is due to mutations across your DNA, right? As I said earlier, this is due to accumulation and the promotion of mutation over a time period across a DNA molecule. So this could be the major reason why a cancer arose. It can be classified, or cancer can be classified into four types. One is carcinoma, where you can expect cancer in epithelial cells. Second one is sarcoma. You can expect cancer in connective tissues like bone, ligaments, etc. Third one is lymphoma, abnormalities in lymph system. The last one is leukemia, where abnormalities in your blood cells, where immature blast cells will be formed due to issues with. What are the 10 different hallmarks or cellular hallmarks of cancer? Hallmark number 1, you see, it is replicative immortality. So, sorry. So, what is replicative immortality? So, replicative immortality means there will be excess expression of telomerase. You know, telomerase is an enzyme which is responsible for the formation of telomeres. During each mitosis, or when a mitosis got over, the size of telomere will be shortened. As a result, the cell division will be stopped. In the case of cancer, there will be overexpression or excess expression of telomerase, So as a result, the telomere length will not be shortened, which is a signal for the cell continually to divide. So shortening of telomeres at the end of your DNA is a signal to stop mitosis. Whereas here, overexpression of telomerase will continually lengthen the telomere. As a result, the cell will think that it has to divide, divide, and divide. So which leads to uncontrolled proliferation, thereby it leads to cancer. And this was first found by a scientist on Hayflick. So, in the name of, or in remembrance of the particular great scientist, it was termed as a Hayflick's limit. So, any cell should not violate, should not cross Hayflick's limit, which leads to a cancer. This first hallmark is connected with the second one, that is instability of a genome. So why telomerase expression has enhanced? That means there should be or there could be some issues in the gene or in the telomerase gene which makes continuous expression of telomerase. So instability of a genome is a great issue in creation of cancer. So what is instability? In the sense, mutations across your proto-oncogenes. There are two parts. One is proto-oncogenes, another one is tumor suppressor genes. Proto-oncogenes are like accelerators, and tumor suppressor genes are like brakes. So proto-oncogenes, example for proto-oncogenes are growth factors. They will enhance cell division. Example for tumor suppressor genes, example for the cellular brakes or tumor suppressor genes, which will apply brake or which will stop the cell cycle phenomenon at one particular stage. Say, for example, when your DNA is highly mutated, a cell cycle should not shift from S phase to the next G2 phase. The error happened in the DNA should be rectified with the help of either DNA polymerase or with the help of specialized repair enzymes. So once repair is over, that is the signal where a cell can shift from S phase to G2 phase. This job was done by your tumor suppressor genes, which prevent the movement of highly injurious or highly mutated or highly erroneous DNA from S phase to G2 phase and thereby to mitotic phase. So it totally prevents the passing of your mutated or erroneous DNA from parent cell to daughter cell. So when there is an issue in the proto-oncogenes, mutations in the proto-oncogenes or mutations in the tumor suppressor genes will cause a great instability across the cell physiology, and thereby your normal cell can be converted into a cancerous cell. So there is no break, but the accelerator will be very high. As a result, uncontrolled proliferation will happen. So that is mutated proto-oncogene, for example, mutated growth factors will continually pass the signal to divide. And here we have to apply the brake. The brake is tumor suppressor genes. And if those genes were mutated, then automatically a car will run without a brake. Third hallmark is again connected with the tumor suppressor genes. Exclusively, two tumor suppressor genes play a major role. So third hallmark is avoiding or bypassing growth suppressor signals. Cell will not oblige growth suppressor signals, or growth suppressor signals will not be generated in a cell. So two different tumor suppressor proteins play a major role. One is retinoblastoma or RB protein. Another one is protein 53, shortly termed as P53. So retinoblastoma protein play a major role in controlling the transcription of your replicatory genes. Replicatory genes such as DNA polymerase, DNA ligase, single strand binding protein, DNA helicase. All these proteins, their respective genes should be expressed only when there is a need of cell division. When you need an expression of any particular gene, central dogma says a gene, if it want to express, it has to enter to transcription and then to translation. So for transcription, elongation factors play a major role. Such a kind of elongation factors of transcription were normally arrested by this RB protein. So thereby transcription of replicatory genes is under control. When this control is out of order, or when your say RB protein is mutated, RB gene is mutated, you will get a truncated RB protein where this RB protein cannot interact with the elongation factors of transcription. So transcription is out of control. Transcription of replicatory genes are out of control. So DNA polymerase, ligase, helicase expression will be very high, which prompt your cell to go for a cell division. Similarly, in the case of P53, what is the role of P53? When DNA is during replication, when DNA is highly damaged, highly erroneous, it has to be repaired. Percentage of error or more number of mismatches occurs automatically. This P53 gene will be expressed. P53 protein will be it will arouse, it will be expressed, and P53, the role of P53 is a transcription factor. P53 is a transcription factor which express one important protein. It's nothing but a cyclin inhibitor protein. Cyclin inhibitor protein expression will be enhanced by P53. As a result, a cell cannot shift from S phase to the next G2 phase. Cell will stay in the S phase for a long time until the repair happens. Now you see these two checkpoints, RB protein and P53, when these two genes were mutated, automatically what happens? A cell can easily shift from G1 to S, that is RB, and a cell can easily shift from S phase to G2, that is P53. The fourth hallmark is because of evasion of growth suppressor signals, automatically a cell gains resistance against death. That means they can bypass, they can avoid apoptosis. You know, apoptosis is a programmed cell death. When a cell is highly injured, even P53 cannot rectify that injury. Automatically, P53 will give signal for the cell to move towards apoptosis through a particular set of proteins. Now you see, there is a problem with the P53. P53 gene itself is mutated. So in a cancer cell, automatically it gains the strength against death. It will bypass apoptosis. How that bypass occurs? Due to overexpression of anti-apoptotic proteins exclusively of BCL2 family and the pro-apoptotic proteins, BAX-related proteins. So those proteins expression will be very high and apoptosis will be prevented, and a cancer cell will not subjected for programmed cell death. Continually it will stimulate for proliferation, or continually it will proliferate. Now this hallmark leads to the fifth hallmark, that is sustained proliferation. So sustained proliferation is nothing but you revisit hallmark 1, hallmark 2, where protooncogenes, it is hallmark 2 is connected with hallmark 5, where hyperactivity, mutated protooncogenes leads to hyperactivity of those proton. Now the mutated protooncogenes will be termed as an oncogenes. So hyperactivity of oncogenes, they are expressed to product oncoproteins, will lead for a sustained proliferation. Now this hallmark 5 is connected with hallmark 6. When more cells are proliferating, they need energy. So you know the best source for generation of ATP is carbon. So we are utilizing glucose for that purpose only. So normal aerobic glycolysis in any normal cell will lead pyruvate during the end of aerobic glycolysis, and pyruvate enters into TCA cycle and ATP is generated. This is normal. Whereas in a cancer cell, there is a slight change in this metabolic pathway. Again, it is an aerobic glycolysis, but glucose will be converted into pyruvate. That is quite normal. But this pyruvate will not be converted into acetyl CoA as if which is happening in a normal cell. Instead, in a cancer cell, pyruvate will be converted into lactate, and lactate will lead to many metabolic products which needs for sustained proliferation of your cancerous cells. So there is a biomass incorporation. So this is actually termed as a Warburg effect, where this was first found by Dr. Otto Warburg. Now, ATP is also generated. More glucose is consumed because the cell is not entering into mitochondria for more ATP output. So pyruvate, the metabolic pathway, normal metabolic pathway, here it stops with pyruvate. So the ATP output till pyruvate, here since pyruvate is entering into lactate, if you calculate the energetics from glucose to lactate, the net ATP will be only 2. So more glucose consumption will be there in any cancer patient. So why a cell is shifting to lactate means lactate will act as a precursor for the formation of many raw materials in a cancer cell, which leads for sustained proliferation. Now, this altered metabolic pathways which fetch the energy, which fetch even the raw material for sustainability, leads to the seventh hallmark. Seventh hallmark is how to escape from immune surveillance. So when cancerous cells start to move in the blood or in the lymphatic system, that is metastasis, it has to escape from immune cells, and not only escape, it should also able to destroy the immune cells. So protection from cytotoxic T cells, nature killer cells, macrophages will happen, or it will be stimulated, or it will be done by your cancerous cells with the help of few specialized expressed proteins termed as protein ligands, PLs. So I'm not going to cover that in this lecture. So once immune surveillance is totally cleverly bypassed by your cancerous cells, next one is it is also connected with the immune system. And inflammation promoted tumors. Tumors will promote inflammation. Your tumor microenvironment will mimic a kind of inflammatory signals which will stimulate the immune cells, which will attract the immune cells by the tumor microenvironment. And the attracted immune cells can secrete two important compounds. One is your cytokine. Another one, it can produce or even it can secrete proteases. Proteases secreted by the immune cells play a major role to destroy the extracellular matrix. Even cancer cells can also secrete proteases. So, along with the tumor cells, immune cells is also secreting proteases. These proteases will damage or degrade the extracellular matrix for effective migration of tumor cells across from one location to another location. And you see, for everything again, how to get energy, how to survive. For everything, blood is the transportation mode. You see, hallmark number 9. Tumor cells cleverly secrete vascular endothelial growth factor. This vascular endothelial growth factors, which was secreted by your tumor cells, can regenerate or freshly generate many microcapillaries from the main blood vessels. As a result, blood will be grabbed and the blood flow will be severe or heavy across many tumor cells. The only the unique feature of the blood vessels generated by your tumor cells is they are highly leaky in nature. Now, finally, so there is an immunosurveillance, genomic instability, altered metabolism. All these things finally make your cancerous cells or tumor cells very strong. Now it is ready to move from its origination to the distant side. So finally, invasion will be activated. Metastasis will start. Metastasis is nothing but malignancy. So this is summary. So here you can see we started with replicative immortality, right? The lengthening of telomeres doesn't stop, which leads to the second thing, which is the responsible for that is nothing but genomic instability. And this genomic instability, right, it leads to the suppression, growth suppression signals that leads to resistance over cell death or inhibition of apoptosis, which makes your tumor cell very strong. And this leads to sustained proliferation. And for sustained proliferation, it need energy as well as many raw material. So metabolic pathway will be altered. And apart from doing this, a cancerous cell should escape from immune system. So that is the seventh hallmark. It is connected with this eighth hallmark, that is tumor promoting inflammation. And finally, you can see angiogenesis stimulation or generation of blood vessels, which leads finally to metastasis. So today we are going to look this hallmark number 2 exclusively proton-oncogenes, or hallmark number 5, 2 and 5, which is highly connected with the proton-oncogenes. So what is the normal growth factor signaling? So here the signal is nothing but the growth factor. So here this circle, mild violet color circle denotes signal. Signal here is nothing but a growth factor. Assume growth factor is an example for proton-oncogene. So growth factor interacts with its receptor. So growth factor and receptor interaction leads to activation of many transducing proteins which are distributed in the cytoplasm. And what these transducing proteins can do, either it can alter a metabolic enzyme, or it can stimulate the expression of a gene, or it can alter cytoskeletal proteins like actin, myosin, kinase, dynein, spectrin, so many other things. So what happens when you alter this metabolic enzyme? That will alter, sorry, that will alter the metabolism. What happens when you create changes in gene expression, altered gene expression, which can totally alter the cell physiology, and by altering the cell cytoskeletal protein, you can pressurize a cell to move towards mitosis. So three different targets, three different angles, what a growth factor can do. So how signaling can happen? Any signaling molecule can pass the signal from outside, or the signal can be passed to the inside. Now here you can see this is cell surface signaling. This is the signal molecule. It will interact with the receptor. See, the signal molecule doesn't enter into the cell. So the signal will be transduced from outside. So this is cell surface based signaling. Whereas intracellular means your signaling molecule can interact with the receptor, can diffuse into the cell, and it can interact with the receptor which is present either in cytoplasm or in the nucleus. So based upon location of receptor, so here the receptor will be present in the cell membrane, but in the second part the receptor may be distributed in cytoplasm or in nucleoplasm. So the growth factor mediated cell signaling, sorry, the growth factor mediated signaling is purely depends upon classification. One, their receptors will be distributed only in the cell surface. So now here you can see what are the functions of growth factors involved in proliferation of cell, differentiation, growth, survival, and even angiogenesis. Now the left you can see these are all classical example for proto-oncogenes, growth factors, their receptors, and signaling molecules which are distributed in cytoplasm like SRC, ABL, RAS, RAW, MAKE. No. So these are of MAKE. These are of proteins, and the growth factors or receptors or these set of proteins are classical example for proto-oncoproteins. The genes which are responsible for expression of these proteins are actually termed as proto-oncogenes. So today we are going to I'm going to discuss about a particular growth factor, that is EGF, how it is interacting with the receptor. So that will be the main part, and the signaling cascade will be minutely discussed, minimally discussed. So you can see a variety of growth factors, EGF, PDGF. So platelet-derived growth factor mainly involves in proliferation of mesenchymal cells. Your fibroblast growth factor promotes your osteoblast, chondrocytes, and few mesenchymal cells. Your epidermal growth factor stimulates the epithelial cells to a little bit mesenchymal cells. So your transforming growth factor will regulate fibroblastic and osteoblastic mitogenesis. So vascular endothelial growth factor, which can stimulate the vascular endothelial cells or regenerate or generation of blood vessels. So PDGF, EGF, FGF, even NGF, nerve growth factor. These are all classical examples of growth factors. Widely distributed or prominent growth factor among these is your EGF. So now these are all the respective growth factors. You can see the receptors. Now, what is the signal transduction? It's a very common outlay. So assume there is a epidermal growth factor. We will take epidermal growth factor as an example. Epidermal growth factor interacts with its receptor. You see, the unique feature is the interaction of epidermal growth factor with its receptor leads to dimerization, which is the unique feature in any growth factor mediated signal transduction. And this dimerization, here you see, leads to autocross phosphorylation. Here you can see this is autocross. One receptor phosphorylates the other receptor and vice versa. Autophosphorylation is different from autocross phosphorylation. Please don't confuse. So here the mechanism is not autophosphorylation, it is autocross phosphorylation or cross autophosphorylation. So this leads to phosphorylated receptor, which attracts two important proteins. One is growth factor receptor binding protein, growth factor receptor binding protein, GRP2, which recruits the adapter protein termed as GEF or SOS, which stimulates your RAS, which is an intracellular or intrinsic protein, and this RAS will shoots or it will activate the next protein, what to say as RAF. Here the same thing. RAF will activate MAP kinase, which activate MAP kinase. This MAP kinase can involve, as I said earlier, it can alter a cytoskeletal protein or it can alter some enzymes. So here MAP kinase better alters cytoskeletal protein. One important target of your MAP kinase is lamin, which is highly distributed in your nucleoplasm. Now, a little bit we will discuss more about EGF. So here you can see this is the structure of EGF. It's a simple protein whose molecular weight is 6 kilodalton. It's made up of 3 amino acids. It contains 2 domains, N terminal and C terminal. And you see 32 residues in N domain, and the rest of the residues occupy C domain. So here you see, I want to emphasize these things. So here you can see this green color, where your tyrosine, leucine, histidine, arginine, glutamine, which occupies in this area specific residues, location specific residues. These residues, as well as isoleucine, alanine, and leucine, that is yellow color, these residues. Finally, leucine. So these 3 parts, green color, yellow color, and red color. So a couple of amino acids which are distributed in EGF play a major role in interacting with the receptor. So even though your EGF is made up of 53 amino acids, all 53 are not involved in interacting with your receptor. A couple of amino acids, say 2, 4, 6, 8, 10 amino acids. So 10 by 53, you see approximately 5% of your amino acids play a major role in interacting with your EGF. If these amino acids were mutated, then your EGF activity will be enhanced, and once if EGF occupies the receptor continuously, the signal will be fired. Here, this is PyMol version. I have simulated the structure in PyMol. You can see it's made up of the beta parallel sheets and helix and loops. And here you can see where your tyrosine, leucine, histidine, arginine, glutamine were present over here. There is green color. There, this green color. This green color portion is simulated over here, and you can see the leucine. So we are here. This part I have still simulated here. This is leucine 47, and this part, your isoleucine, alanine, and leucine was simulated over here. The overall picture, again, the overall picture. So this is your C terminus, and this is the N terminus. Now, the structure of epidermal growth factor receptor, or structure of any growth factor receptor, can be segregated in three different domains. One is your ligand binding and dimerization domain. Second one is highly hydrophobic transmembrane domain. Third part is your receptor tyrosine kinase domain. And here you can see receptor tyrosine kinase domain is present in C terminus of your growth factor. Ligand binding will be present in the N terminus of your growth factor receptor. So here you can see the extracellular ligand binding domain and dimerization arm composed of 621 amino acids. You see, structure of epidermal growth factor receptor is too bulky. It contains 1186 amino acids. So out of this 621, at least half, 50% of your growth factor receptor amino acids were distributed in your ligand binding domain. So you can understand the impact or importance of your ligand binding domain. So this domain is classified into again 4 subdomains. Again, subdomain 1, 2, 3, and 4, or extracellular region can be classified into domain 1, domain 2, domain 3, and domain 4. Domain 1 and 3, they are very important, highly enriched in the leucine. They are responsible to interact with your growth factor, that is EGF. Domain 2 and 4, they are responsible for formation of a disulfide linkage. That means they are enriched with cysteine residues, and these domain 2 and 4 are responsible to interact with the transmembrane parts. Now you see, transmembrane part is the shortest portion of your receptor. It contains only 23 amino acids, hydrophobic in nature. The rest, again, at least say another 45 to 50% of your receptor portion was occupied by your intracellular domain, 542 amino acids, huge, which contains the tyrosine kinase domain. And this tyrosine kinase domain again is subdivided into N lobe and C lobe. Between N lobe and C lobe middle, there will be ATP binding sites where phosphorylation occurs. So now again, this is a PyMol visualized structure. You can see domain 1 and domain 4, they are cross. Domain 2 and domain 3, they are cross. So you should not mimic like 1, 2, 3, 4 like this. So 1 and 2, this is 4 and 3. 3 and 4 is swap. So 2 and 4 are diagonal, 1 and 3 are diagonal. So you can see, already I have mentioned domain 1 and 3 of your growth factor receptor, extracellular domain of your growth factor receptor, domain 1 and 3, they are enriched with the leucine. So leucine is highlighted in blue color. Domain 2 and 4, already I have mentioned, they were enriched with the cysteine. So the gray or white color, which is highly visualized here in the red background, you can see they are all cysteine. And here you can see the very short, simple 53 amino acid short oligopeptide, that is your epidermal growth factor. See this part, it is going to interact with only 1 and 3. So you see, EGF is not interacting with the 2 and 4, it is interacting with 1 and 3. So this you have to understand. If we are going to block this interaction, we are going to design a suitable ligand in a cancer cell, in a cancer patient. We are going to devise a ligand to inhibit this interaction. We can stop the cell division. So what is the dimerization when EGF interacts with the receptor? Dimerization will happen, but normally this dimerization is not happening. How? You can see there is an auto inhibition of dimerization. This part here you can see. So domain 2 and domain 4 is responsible to inhibit this dimerization. Exclusively the tyrosine, which is present in domain 2, interacts with aspartate and arginine of your domain 4. This prevents the dimerization of any receptors normally. Remember, dimerization should happen only when growth factor interacts with the receptor. When growth factor is not occupied, dimerization should not happen. So how this auto inhibition happens? That is purely because of interaction of tyrosine in domain 2 with aspartate and lysine of domain 4. Shortly it inhibits. And once when growth factor occupies, when EGF interacts with the receptor, there will be a conformational change which disconnects these interactions. As a result, the dimerization arm will be exposed. Now your EGF occupied receptor can interact with another EGF occupied receptor. As a result, dimerization will happen. So now here you can see. So now you can see this is one monomer. This part. So this is one monomer. This is another monomer. This happens only when a receptor interacts. When once receptor interacts, automatically we are expecting the autocross phosphorylation. Earlier we have discussed now. How this happens? Because of a latch formation. What is this? So here you can see this is a monomer. This is the receptor. Now here this is growth factor. This is growth factor receptor. Now when once happens, there is a change in the receptor and the dimerization arm will exposed. Now you can see it interacts with another EGF occupied receptor. Here carefully you see the receptor. Now you can see it is crossing. This is actually termed as latch. This is actually termed as a latch. So this during this latch formation, now here you can see it is an activator. One receptor will act as an activator. Another receptor will act as a receiver. Both the receptor, remember, this latch formation will make one receptor as activator, another receptor as a receiver. Now the activator, the kinase domain of the activator, the tyrosine kinase domain of this activator will phosphorylate tyrosine residues of another receptor. Once the tyrosine residues are phosphorylated, the latch will be reversed, right? Now this receiver will act as an activator. Now activator will act as a receiver. Now the tyrosine residues in the next receptor will be phosphorylated. So please understand, both the receptor contains tyrosine residues in the cytoplasmic end. So the receptor, the tyrosine kinase domain distributed in the cytoplasmic portion of the receptor will act as an activator, right? It will phosphorylate tyrosine residues of first of one receptor, activating it, and then the activated receptor in turn change. It will phosphorylate the activators. So this is a very tedious concept to understand, right? Now here you can see very clear cut. So this is one receptor. It will act as an activator. another receptor. It will act as a receiver. So this receptor will have tyrosine residues. These tyrosine residues will be phosphorylated by the kinase domain of this activator receptor. Now once the phosphorylation is over, the latch will be changed. Now the receiver will go here, the activator will come over here. The receiver part will be converted as an activator, the activated part will be converted as a receiver. Now this receiver, again it will be phosphorylated. So both the receptor, the tyrosine residues distributed in both the receptors will be phosphorylated. Here you can see, so you can see this receptor. Now the green color part, carefully you watch. So this is the receptor. So you can see I'm coming over here. So this part. So this is the receptor. So this receptor, right? Now here you can see, here you can see. So this part here you can, sorry, this part. So from here, this part, yes, this. Now you can see this green. Now this is the latch. It will activate. Now the topology of this cross will be changed. This blue will become green, this green will become blue. So as a result, both the receptors, their tyrosine kinase will be activated. So now here you can see, right? So this is the receptor tyrosine kinase. These are the tyrosine moieties which are distributed. So many tyrosine, 703, 920, 974, 1068, 107, 86, 1173. These tyrosine residues distributed in receptor domain will be phosphorylated, will be activated. Again, here you can see, right, a full-fledged sketch. Binding of EGF activates the receptor, the transmembrane domain will be activated, latch formation, and finally the receptor tyrosine will be phosphorylated, you will get phosphotyrosine. Now you can see this phosphotyrosine can attract many signaling molecules, growth factor binding domain, phospholipase, too many other effector proteins. And one important thing is growth factor binding domain can stimulate this SOS or guanosine exchange factor, and this guanosine exchange factor, it will activate RAS. Very simple, GDP will be exchanged with GDP. Simple. Now RAS GDP will be active. So what it will do, the activated RAS, it will recruit one protein, it will activate one protein termed as RAS activating protein. This will activate MAP kinase, and you can see this MAP kinase, and that will MAP kinase will activate MAP kinase, and MAP kinase finally phosphorylates. You can see MAP kinase is a serine 309 kinase which targets many cytoskeletal proteins distributed in the nucleoplasm, exclusively lamins, and thereby cytoskeletal distortion will occur. Now your nucleoplasm, the nucleus will be destabilized, exclusively nuclear membrane will be destabilized, which leads to disintegration of nucleus, which is the start of disease. So friends, little bit I would have rushed, kindly bear with me. The main aim of this task is, or this talk is, how a growth factor interacts with the receptor. The rest of the part can be easily understood, but the first primitive thing, how a growth factor interacts with the receptor, and what are the different hallmarks, how one hallmark is connected or how one process is connected with another process. So that is the main aim of this task. Thank you for your patience. Thank you.